Hello everyone, my name is Michael. I lead business development at Native Robotics. We are a software company and we create apps for robots. Or at least we would like to be a software company, but cruel reality often pushes us to solve a bunch of mechanical, electrical, and vacuum challenges. Today I want to share with you several hard-learned lessons on how you can make a palletizer of your dream. And also show you the latest app which we developed, OmniPack, app for palletization. We will go through four parts. We will start with what data you need for your palletizer. Then we will cover typical hardware requirements for your palletizer. Then I'll tell you about a holy software grail of every application. And finally, I'll share a couple of real-life installations which we did. Remember that everything in your palletizer is interconnected. Your design determines limits of applicability for your palletizer, and the right one has fewer limitations. You should look at these four areas first: general frame design, column, gripper, and software. Design starts with a data request. You can see a list of important parameters which you need to know up front. Feel free to download our template from the link above. This template will be really handy when you have many layouts and you need to find out which variables may cause you problems in the future. Key thing here is to cross-check to make sure your palletizer will work for all layouts you need. For example, in layout 1, you see that you need a really tall pallet with a relatively high cycle time. This can mean that you will need to carefully consider the speed of your column. Hardware. If your pallets are shorter than 4.6 feet, you actually don't even need lifting columns and you can get away with fixed pedestal for most of the cases. If you do need to palletize higher pallets, then conceptually you have two options. Either you go with a heavy-duty rail type column, or you can go with a standard telescopic mobile version. Both solutions have pros and cons as well as applicability limits. As a very approximate rule of thumb, you can say that if you have a relatively tall pallets, heavy boxes, and demanding speeds, you should go with a rail design. On the other hand, if you need a palletizer to be mobile and don't have challenging weight or speed requirements, you can use a telescopic column design or just a fixed pedestal. Let's have a look at the mobile option first. With a mobile frame, you have to note three parameters: length, width, and height of your frame. The references I'll give you are approximate and also depend on your gripper and box size, but still quite useful. Similar frames can be used with fixed pedestals. Let's start with the width of your frame. It impacts the stability of your palletizer as well as possible wrist frame collisions. As a general rule, you want your frame as narrow as possible, as it directly constrains the working area of your robot. Another observation is that every inch cut off the frame gives you space to place a box 1 inch smaller. So it's quite impactful. A good example of a problem you can see on the slide. Depending on the order in which you palletize boxes, your layout and box size can get a collision. You can get a collision between the wrist and the frame. This happens when the robot goes down to place the box or up to pick the next one. It is true that you can solve this with software, but logic becomes very complicated very quickly as soon as you have more than one palletizing layout. So to be on the safe side, just keep the width as small as possible. Next parameter is the height in the home position. This will impact reachability of your robot and also the minimum height of the boxes you can palletize. In general, the height in the home position should be below 41 inch if you're working with a UR10 series of robots. Finally, the length of your frame. It will impact the maximum height of the box you can pick. As a rule of thumb, you want to keep the elbow angle below 130 degrees. This usually becomes a constraint when the robot lifts the box from a conveyor. A rail-based frame is a bit less tricky than a mobile one, and I believe is more suited for the North American market due to the pallet size. With this in mind, reachability is usually the biggest problem. However, a solvable one. For example, if your robot can go as low as your pallet, you can easily reach the pallet corners with small boxes even without the TCP extension. On another hand, if you want to find a balance between the column stability and workspace restrictions, as a rule of thumb, you want to keep the width of your column reasonable to avoid joint collisions when placing boxes behind the rail. Similar rule applies to the length of the guide car. You want to keep it as long enough so the robot can reach to all corners without joint rail collisions, and at the same time it needs to be short enough to avoid bending too much. Let's talk about the column now. Apart from geometry, which we covered on the previous slides, you are looking for 3 additional characteristics. These are important for rail and telescopic columns alike. First is twist resistant. This is important as your robot basically is a giant lever with a massive box at the end. Every time your robot starts or finishes a movement from a conveyor to the pallet, inertia will twist the column. Physics is heartless. Another point is vibration resistant. This is more relevant to telescopic columns as the robot is always fixed at the end of the column. Again, each movement of the robot will generate mechanical waves in the structure. They will propagate down to the ground and then reflect back and come to the robot. These 2 points can significantly impact the well-being of your robot as well as general performance. For example, the robot will try to compensate for small displacements and this can generate unnecessary peak current in the joints. Also, if vibration persists, you can end up needing to recalibrate pick and place points as displacements accumulate. The last but not least is column speed. It plays a vital role in determining cycle time for tall pallets, as usually the column is much slower than a robot and total cycle time goes up. The last 2 notes here: if possible, always consider installing a buffer for boxes on the conveyor. Robot usually palletizes lower layers faster than the top ones, so a buffer will help you keep the production speed the same. Additionally, if you are looking at the telescopic columns, we would suggest taking the columns as wide as Evelik's SKF version, but not smaller. Otherwise, the vibrations and twists are too severe. Finally, keep the base of the robot horizontal to the ground. Any non-horizontal position of the base is just non-optimal from the mathematical point of view, and will also cause you a lot of problems during the programming phase. This last bit took us a while to figure out, so if you're interested to learn more about the mathematics behind it, definitely reach out to us. The final piece of the puzzle is your gripper. This one is relatively simple. You need to minimize the size of the gripper to avoid collisions while maximizing the grip area to ensure good pick. Also, you want to make sure your gripper is as light as possible as payload is limited. Additionally, remember that peak release time will significantly impact your cycle time. Blow-off functionality becomes very important here as well as good vacuum. Good vacuum will allow you to pick porous boxes as well. So typically this is a big issue. Finally, note that even though you can extend your TCP, it doesn't come without a cost. If we are talking about a point mass, additional 500 millimeters of displacement will reduce your payload approximately to 5 kilos from 10. And if you account for movement inertia, generally non-uniform mass distribution inside the box, even 100 millimeter displacement can significantly cut your payload in some cases. At this point, you probably feel quite confused about why this is so difficult, but don't worry, we have useful tools to make your life easier. For example, you can use our free web simulator, which is available on PC. Use this link to access it. You can do reachability studies here, check cycle times with universal robots, though approximately, and make sure your robot performs well in general. Drop me a message if you'd like to see your hardware inside this simulator. Alright, we've covered the hardware part with you, let's talk about the software. Software is the brain of your application, and typically you're looking for the holy grail. That means that your software has to be flexible and user-friendly, it has to optimize performance of the robot or at least make the operation efficient, and it has to be easy to troubleshoot. From our experience, you usually cannot achieve all all of them at once, maybe only one or two of them. But let me show you how we as native robotics get to the Holy Grail. There are three tools which you can use to get there. You may teach the robot how to palletize on your own by using Polyscope or offline programming software. Alternatively, you may use a new approach. You can take an advanced, user-friendly app for your application and install it on your robot, the same as you do with your smartphone. The last option is what we do at Native Robotics. This app approach is actually the quickest path to our Holy Grail. It's packed with super benefits like native tasking and predefined error handling. Moreover, we have invested 10,000 hours developing each of our apps, which is impossible if you program a robot from scratch. Let me show you how it works. Our app for palletization is called OmniPack, and it consists of two components, hardware and software. From the hardware side, a small industrial PC is a home for OmniPack. The PC is connected to Full HD external touchscreen via HDMI cable. This touchscreen is an interface for the user. PC also is connected to the control box through the Ethernet cable, and OmniPack controls the robot in almost real time. You may ask, why do you need a second screen or a second PC? A short answer, so we can unleash superior processing power and design the apps the way how it's convenient for the end user. Also, you won't need a PhD in robotics to be able to work with the robot. Let me show you how the magic works. On the screen, you see how a palletizing robot is configured in the plant. It's completely intuitive, with 0 lines of code. Any worker can reconfigure the robot in just 5 minutes. We still have advanced settings inside, which allow us to adapt to any situation on the plant. And that's how we get to the first part of the Holy Grail. The second part will be efficiency and optimal performance, but before I go there, let me explain what does it mean optimal for the robot. The key here is that optimal is different in the world of a robot, which is 6-dimensional spherical space, versus our regular 3-dimensional space. How different, can you ask? For starters, let's look at the angular speed in one of the joints during two movements, linear and a free TCP movement. This is what you will see. In order for the robot to support linear movement of the TCP, it must quickly change angular speeds in the joints. That's what you see in the red line on the right. In contrast, if your robot uses free movement, angular speeds stay more or less the same during the whole action. Why is this important? Because sharp changes in speeds mean high acceleration and jerk. High acceleration and jerk mean high electrical and mechanical stress for the robot, which decreases the robot lifespan. This does not mean that you should not use linear moves, but it does mean that you should be careful programming your robot. Now let's get back to the second part of the Holy Grail, optimal performance. In your typical palletizing application, you would see two moves we discussed, linear and free. However, as you now know, our robot is not too happy about these trajectories and would prefer to roam with a constant speed in joints and in order to live longer. Moreover, when you switch between different movements, the robot has to go through a start and stop cycle, which is also not so good. The same as with your car, for example. And this is exactly what we can fix. Instead of using square trajectories, we have a motion planning algorithm which will generate an optimal trajectory for your robot. Optimal will mean smooth trajectories, reduced acceleration, and a happy robot. Here's how it looks in real life. On the right, you see a simple linear to free trajectories, and on the left is our motion planning. Notice the difference in trajectories and general robot performance. The moves are smoother, accelerations are smaller, and we still finish the job 20% faster. And a sharp-eyed listener can even notice how the robot damps the inertia of the movement with a gentle wrist move. This is how we get to the second part of the Holy Grail, efficiency. Finally, the last part of the Holy Grail is troubleshooting. Usually error handling for the end user is quite effortful. Well, suffer no more. Most of these issues Protective stops, vacuum losses, pallets and box checks, buttons, lights, and all other things. They are already there. Just press the correct button on the screen and that's it. Your robot is ready to rock. So we acquired the Holy Grail. We can set up a palletizer in less than 10 minutes. We can optimize the robot and prolong its life. And we can even ensure reliable operation and easy troubleshooting. What does this mean for the business? It means 50% operational cost decrease for your robot. Your robot became as easy as your smartphone. And you usually don't write applications for your smartphone or computer. So why would you do that for a robot? Jump into the future with us. I'm sure at this point you're skeptical. It's all too good to be true. So let me support my claims with our finished projects. This is a project which we did together with an integrator company ANT for a leading coffee seller in Eastern Europe. We installed 8 palletizing stations which were interconnected with each other, and each of them used OmniPack to control the robot and the 7th axis. We used rail-based design as we have to make 7+ feet pallets. Each station has more than 100+ layouts inside and communicates with several external devices, conveyors, PLCs, and even AGVs. The next example is a mobile palletizer for a 3PL service provider. Customer needed a very fast palletization for heavy and tall boxes with a relatively slow column and a weak vacuum. As a result, if you use standard trajectories, the robot will start launching boxes across the warehouse at every stop point. Flash royale of all possible problems. But with motion planning, we can do Tai Chi magic, which you see on the screen. Movements are smooth and operation is exceptional. I especially like how it reaches out for the cardboards. And the last example is from one of the leading integrators in Spain, Ince Robotica. The guys are professionals in the end-of-line automation and have been working with industrial robots for 50 years. They were using their own software called Mosaicus to generate the code for a robot, but after seeing OmniPack, decided to integrate it into their collaborative cells. Here you can also see our motion planning in action. The client had small boxes and relatively restricted space. You see we have a conveyor on the one side and cardboard warehouse on the other. But with motion planning, we can avoid all these obstacles and still keep optimal performance. Some time ago, this cell was installed on the client side, and software-related commissioning took less than an hour. Basically, the guys needed to recalibrate, pick, place, positions, and that's it. The robot was ready for operation. The client was very happy with how easy it is to interact with the robot and gave us A+ on the feedback form. It's always a pleasure to hear that from our partners and clients. So, today we went with you through the major hardware and software challenges which you can encounter, and even got a holy grail of every robotics application. For now, just for palletizing, but soon for many other apps. If you like what you saw, please feel free to reach out to me directly via mk@native-robotics.com or using the links below. We are now looking for the integration partners and would be happy to support you from the software side of things. And if you are an end user and want to see a palletizer like this at your plant, also don't hesitate to reach out and we will help you get a palletizer of your dreams. Thank you.